Good morning, everybody. So I want to take a little bit of time to make this video about the Newton's second law assignment because this is mostly, with the exception of question 4, this is all practice to get you ready for the final force and motion assignment, which is going to be happening in class on Thursday or Friday. If you're in fourth period, you'll be starting the final assignment, which is a Lilo and Stitch investigation, tomorrow on Thursday. If you're on your own in the asynchronous time and finishing it up in class. If you're in second period, we'll be starting it as a class and you will use your asynchronous time on Friday to finish it up. So I'm going to take some time and I'm going to split this video into 3 different videos to go through questions 1, 2, and 3 on this video. I think I'll talk about question 4 as well on this video and just give some overview about what I'm looking for. On the next video, I will go over these force diagrams. That'll be questions 6, 7, and 8. And then on the last video I make, I'm going to talk about this part 2, understanding the equation F equals ma. And so that's questions 9, 10, 11, and 12. So I will start with question 1 right now. Okay, so I went along and I opened up the PhET simulation and this one side by side. Question 1 is asking us, click on the net force, play with the simulation in order to explain how the motion is different in 2 possible situations. When the forces are balanced, that is the sum of forces equals 0, or when the forces are unbalanced. Use those words in your answer. As I'm playing around with this, I can make a balanced force when I see that the sum of forces is equal to 0. When I press go, I see that though these two people are exerting a left and a right force, they're exerting an equal force. So the applied force in both directions is equal, therefore it comes out to a sum force of 0. This is like saying 100 newtons plus negative 100 newtons equals 0. The cart does not move. I can get the cart to start moving when I made the force unequal, but then when I made it equal again, the speed did not change. So my answer is that when the forces are balanced, the cart will either not move or it will move at a constant speed. When the forces are unbalanced, I see a sum of forces that is not 0. I see that the cart is moving in the direction of the larger force and it's speeding up. That's what I would say for question 1. Here's that written down here. So when the forces are balanced, I see that they cancel each other out and the cart stays in the center. Or another way, when the forces are balanced, it's not moving in any direction at all, or it's moving but not changing speed. When the forces are unbalanced, I see that the cart moves in the direction toward the larger force and the speed is increasing. The cart is accelerating. So question 2 is asking us to change to the motion section, apply a force, and then take it back down to 0. Why doesn't it stop, and how can you stop it? So I can apply a force, and then I take it down to 0. So the reason that this doesn't stop is because this is a magical land of no friction. So there isn't another force that's pushing back on the cart in the other direction. Therefore, in order to get this cart to stop moving, I need to apply a force in the opposite direction to slow that back down to 0. And I'm watching the speed dial there and just kind of pressing on the cart until I can get that speed to reach 0. So there we go. When the force is brought back to 0, the cart keeps going because there's no friction pushing back on the cart in the opposite direction. I could stop it by applying a force in the opposite direction that I did originally until the speed reaches 0. Done with 2. Now move to friction. This time, when you apply a force and then take it back to 0, the box stops. Friction. There we go, the box stops. It's not magic, that's friction. So set up a scenario where there's a force applied but the object or objects don't move. So I'll go ahead and let's stick a couple boxes on top of each other. I'll put this man on top of the boxes. And I'm going to go ahead and push with a force of 150 newtons to the right. So here's my applied force of 150 newtons to the right. You can see that in my force diagram, I have 180 kilograms. That's 80 plus 50 plus 50. I drew a box to represent that. And I have my 150 newtons of applied force going to the right. Now, as we can see, it's not moving because the friction force is pushing back. Basically, this box is on kind of a gravelly surface, and it's really hard to push on that surface because there's just tons of friction. There's tons of force that's keeping it from moving. So that friction force is 150 newtons that's keeping this box from moving. Now, just so you know, if I bring that friction down, like if it's sliding on ice, this is why it's so much easier to push things on ice. There's very little friction on there. Now, of course, this is fake. Maybe there's a tiny bit of friction on there. Okay. So if the forces, so the object isn't moving because of the law of inertia. Now, we actually didn't talk about this law, but this is basically stating where there is an equal force acting on an object in the opposite direction. So the sum of the forces equals 0 newtons. If the forces are balanced, this goes right back to question number 1. If those forces are balanced, it's not going to change its speed. So if it started at 0, it's going to stay at 0. That's questions 1 through 3. Now, I spent some time during the asynchronous meeting yesterday, and during fourth period during class, talking about question 4 of really what I'm looking for. So I'm going to stay in the friction, and basically you have the sentence frames here for making the claim in response to this question. So how do we predict an object's change in motion? What kinds of things can cause an object to change its motion? So I showed that if I have a 100 kilogram box, okay, and I apply 200 newtons of force, this box doesn't move. So we spent a little bit of time brainstorming ways that we could make the box move. We could increase the applied force to get it to move. We could decrease the friction to get it to move. And I have to reset everything. Okay, or we can decrease the mass. So these are 3 ways that we can get this object to move. Now, based off of that, if you were given some scenario, right, we have a box. I'm going to go ahead and press pause so it won't move as I do this. And I'm going to apply a force, and I'm going to reduce friction. Would this box move when I press play? What's your prediction? Why do you think that? Based off of the observations that we've made before. So we can predict whether or not an object's motion will change based on, and you'll state your answer, because we observed that blank affects the object's motion when, and also the simulation showed us that blank causes blank. These observations led me to the claim that, and then you'll repeat yourself a bit, because, and you will restate how the science works there. Okay, so that's question 4. Remember, you can answer question 4 with an audio response if you prefer to speak your answer. Okay, that's this first video. For the next video, I'm going to go through questions 6, 7, and 8.